Thank you for coming and having great two conference organizers. A little bit of a different talk from the previous ones we've seen all day, actually. We took our VR study and kind of made a scientific study of what we've been looking at General Motors, applying full body motion tracking and VR-based ergo analyses. I started this off. I'm going to give a quick GM overview, and we actually had Ontario Tech University do finish up this research study for us. They're a university just located right just outside Toronto, Canada. So why VR for ergo? It embodies the DHM, which I'll talk about in a little bit, the digital human model in real time. We can interact with parts and tools as we're designing new vehicles. We're able to conduct all types of ergonomic studies, which I'll touch on. It alleviates the need for posture prediction, which actually takes us a long time to do when we're sitting at a desktop using a mouse and kind of guessing at posturing. So we tend to see some subjectivity in that, and we'll see some errors comparing what an operator might actually really do in the future when we've tried to predict their behaviors or their postures. It leverages the first-person movement behaviors. So when we're interacting, we can literally act out the operator on new vehicles, especially vehicles we haven't built before. We could proactively evaluate joint and spine loading, all types of different ergo analyses that we do on a day-to-day basis at GM. And we can integrate several software programs. So we're using software like Siemens Process Simulate, ICIDO by ESI, Unreal, and Unity, just to name a few. These are a variety of DHMs out there. There are also people creating their own, maybe in Unreal or Unity. GM is currently in our manufacturing ergonomics process, which I'm going to speak about. We are currently using the JAC model from Siemens Process Simulate. Why do we use them? They're really the platform for advanced ergonomics assessments. We look at things like posture prediction, strength demands for a population, fatigue estimation, and the human factors group will look at comfort assessments as well. Also work simulation and process design. So we'll look at different percentiles of humans who can do the job versus a 50th female maybe for reach or a 95th male for hand clearance. We also look at vision requirements and of course virtual reality simulations, which I'm going to be talking about today. The importance of VR assessments, pretty critical, even for the virtual assessments that we do like in math way up front. Identifying the issues is very important for us very early in the program. We have teams running VR builds, even turning stuff on and off in math data as the designs are being done almost in real time. So very important to kind of move this and proactively look at the designs up front using as many virtuals and simulation tools we have. The benefits for this are pretty obvious. We have 3 stages of the vehicle. Pretty much they're narrowed down to about 3. Virtual, pre-production, where we're building prototypes, and of course launch. And our process, it really fosters collaboration between designers and manufacturing engineers, and we want that to happen way early in the design stage using these tools. It's literally almost no cost to make changes to parts, make stuff fit, improve performance very early in the initial stages. As you move towards pre-production, where dies are cast and things have moved pretty far ahead, the cost increases. So as you get closer to the launch, very high cost, and the opportunity for change is much lower. At that point, we're not really moving stuff around in CAD. We actually are looking at, drilling holes and doing workups on parts in the prototype stages. So for that, we really focus on what we call solutioning to the left. Our current workflow in manufacturing ergonomics it's all performed on the desktop. It's pretty much all static assessments. Those are kind of like the big 4 listed there, what types of analyses we're doing for the operators that build our vehicles each and every day. Limitations, not a true, that static analysis, that kind of one point in time, isn't a true representation of forceful dynamic tasks. As I mentioned earlier, the posture prediction is not often consistent on what the operator may end up doing. And there's lots of unknowns, kind of like that guessing in 2D, is you can move some things around the environment, but you don't exactly know what's going on if you can't act it out and get into that posture. Just a quick overview on why we've added VR to our Ergo process today. It provides an early assessment of potential ergonomic risk of future products. We can collaborate during virtual reviews with various teams in product design, service, manufacturing, pretty much everyone. This was very helpful during COVID, where we were working from home, and we could pretty much broadcast reviews through Teams or Zoom. Line of sight is a pretty big deal because that's one of the things we don't really have very good algorithms or models on, or other people for that matter. So this has paid dividends for just having that vision analysis. Tracking full body motion, which is the talk today, to assess complex postures. We'll get into that a little later. And then, of course, some basic reach evaluations. So some of the current challenges come with VR. They are so critical. The hand and body tracking are so critical for manufacturing ergonomics. It's even affected like mainstream adoption. So where we really need to act out and be the operator to kind of try what they are going to experience. Some of the things I have up there are real things. Motion sickness, physical discomfort with just wearing the headsets. I talked about the body tracking technology being as realistic as possible. We look at, we've used optical and IMU-based tracking options in the past, and then the fidelity of the ergonomic assessments and recommendations. Is the operator's position in space actually mimicking what's being shown in VR? And if we're doing a job in VR, how close would that be to physical reality? So am I actually placing the object where it needs to be placed, or doing my lifting analysis and lifting it where it needs to be placed? Our current tracking modalities at GM we're using the Vive within Siemens just to capture data for most of our simulations. Cost effective, pretty much an integrated solution with the Siemens and ICIDO softwares. Cons, some disadvantages might include it doesn't have the fidelity for the complex biomechanical analysis, or some of the research that you've seen done with IMUs. There's a lot out there on like exoskeletons and wearables, or validating all of the new AI that's coming at a pretty rapid pace for Ergo. We also have a couple, actually 3 or 4 of the XN suit. So this is that IMU option. This will give us a very advanced biomechanical model. It has 17 sensors to pick up all kinematics. We have put these on operators in the plants and taken data before. It's occlusion proof, right? You can get in and out of a vehicle, close doors, assess comfort, ingress, egress studies. You don't have any cameras. There is some bad with this. There's sensor drift, still a pretty big issue in the IMU world. And then some errors estimating joint positions, really because the position of the product. So for this type of technology, it's really hard to sync up the position with the vehicle. And that's what we do, right? We keep the vehicle at 0, 0, and the body may drift away. So where we do not care about the math data or the vehicle per se is a good use cases when we're just using IMU. So what I wanted to do at GM in my lab was test both tracking systems and measure the hand locations and torso angles. So that's really the bread and butter when you're doing an ergo analysis. Some of it's joint angles, but the big part of it is where my hands are in space. So there's all kinds of literature and studies out there and applicable tools that measure, tell you how much back compression you can have throughout the day, or what are your metabolic limits, or push and pull limits. We have to know the operator's hand locations, the distance from their hands to their spine, and then obviously the vertical heights of their hands to the floor. So we wanted to know what would be the most accurate out of when using both systems. So making the human movement look decent, we've also been looking at this new at the hand locations in AI and new computer vision technology. So it's great that they're showing all this, but how accurate are those hand measurements when they're, making a decision on a risk analysis tool? So this is like a basic, hopefully that plays here. Should be playing. So this is a basic mock-up of what we did in our lab. Pretty crude. We were wearing the Vive and the XNs and streaming this into Siemens Process Simulate, and they have kind of like this interactive ruler to measure that H and V, horizontal, vertical hand locations. And what we did was just pass it through our ergonomics envelope and just kind of look at the worst cases throughout the envelope for reaches. So overhead, kind of at like the corner of each intersection within the envelope of our primary, secondary zones. Won't spend a ton of time on the analyses here, and we don't have to dive into it, but what the results show is they're just represented as a deviation from the target, that target being in the ergonomics envelope. And the takeaway is that percentage of error for each zone. What we were trying to do with this quick test was to determine how much error is too much error and where most of the discrepancy would fall within our traditional ergonomics envelope. So we kind of put them in bins. So where would we be greater than 90 millimeters off, for example, or what we call the green zone from 0 to 29 millimeters. And these zones were just kind of made up for now, but we would like to get to a point where, okay, if we are off 30 mils, is that okay to make an ergo decision? Can we use VR to actually make sound decisions for the operators and make a call if it will be safe for them? So both systems showed error in hand locations relative to actual positions. The errors weren't consistent across all positions in the envelope. Most deviations occurred in the 30 to 60 mil range. And as I said, is this functionality relevant to the analyst? Like, could we analyze spine compression or joint torques if we're kind of in that yellow or orange zone? So what we found, we definitely needed some additional research and a controlled study, and that's where Ontario Tech, we partnered with Ontario Tech, and that's where they came in. So how accurate are the variables of interest when we're using different modalities, the XNs, and we added the optical system, Vicon, as well as the Vive. And that's kind of schematic for the horizontal and vertical distances, how we calculated those. We added another one, lateral hand locations, very important for getting a kind of like a proper accurate representation of a DHM, but not a measurement that we use in traditional like pen and paper tools. So this was the data collection. You'll see we had 16 participants, different heights, different genders. They were wearing the Vive VR headset and trackers, XN sensors, and Vicon optical marker set. So they were loaded up with 3 sensor sets, and they were all taped on. It could, and then you could see the protocol, the operator, this could really be an assembly task. And what we had them do, like putting on a hose, what we had them do is just put their hand through different locations in a reach zone, just moving that through space, and analyze, do the errors get worse if the hands goes up or forward, sideways, etc. We had 9 targets and 3 different like table heights. So we had those kept static. You can kind of see the tables there. This might play in addition. So the data flow in the analysis, just wanted to clarify. So we used a motion capture system. It was an optical motion capture system made by Vicon, and we use this to determine our ground zero. So you hear about that a lot in kind of like the ergo world and digital human modeling, and like I said about AI now. What is that ground truth? So optical systems, traditionally, most universities have them in biomechanical and ergonomics lab. that kind of gives you that ground truth of HV and L. They have sub-centimeter accuracy. So we use that to kind of get our HV and L measurements. And then we also use optical again as we passed it through the Siemens model. So what you see in the center would be a skeleton represented by Vicon, the skeleton represented by XSENS, our IMU, and then also the Vive, and we're passing those through the process simulate model. So we extracted the hand locations from process simulate from each skeleton. Quickly kind of go through the results here. On the left, it just represents the overall error across the conditions we tested. And this speaks to the overall accuracy of each system relative to the actual hand locations. So you can kind of see the Vive actually performed the best. Overall error was 79 millimeters, 40 millimeters better than XSENS, and 11 millimeters better than the Vicon model, not the actual kind of raw data from Vicon. On the right, that just shows the actual horizontal distances. So we're just talking about horizontal reach. You can see in the top right diagram there. The dotted lines were those actual real measurements compared to the horizontal distances produced by the 3 tracking systems. Again, as I said, Vive had the lowest error with 8 centimeters. Overall error of 8 centimeters, Vicon 1 centimeter more, and XSENS had 4 centimeters more error. The larger XSENS errors were driven by underprediction of horizontal at the low and mid-vertical distances. For the vertical distance, the Vive also had the lowest error, about 12 centimeters. Vicon had 3 centimeters more error, and XSENS had 16 centimeters more error. So the larger errors from the XSENS probably driven by an unprediction of the H values at all of the vertical target heights. All systems remained pretty consistent though as the reach increased and they had to move forward or flex forward with their spine. Lateral distance, not going to spend a ton of time on this one. They were fairly consistent. Vive again though, that's that the right-handed movement would be towards the right, sorry, and then the left would be the negative values. Vive again performed with the lowest amount of error, just about 20 centimeters off the real life values, compared to Vicon with 4 centimeters more error, and XSENS had about 3.5 centimeters. So pretty close on those. We also looked at joint angles. So very important for representing, making like new skeleton models and doing some ergo analyses. So I would say look at the trunk, draw attention that the spine flexion angles were quite similar between all systems and predicted very well with all the heights as we even increased in reach. So they stayed pretty consistent. However, that was not the case for the elbow and shoulder. They were kind of all over the place. Probably suggests that the discrepancy between the system could be driven by how the process simulate, the software is computing the skeletons themselves, right? Because each different tracking modality with the collections of markers builds their own skeletons and streams it into process simulate. And there's been plenty of research on this IMU system in particular that shows the joint angles are actually pretty accurate to ground truth angles as well. So it is likely the software we're using for the difference of angles. The other thing may be because of for the hand positions as well. For the Vive, we're actually holding the controller in the hand, where the XSENS, the IMU sensor, is sitting on top of the hand. The marker set for Vicon, I believe it's a cluster of markers just on top of the hand as well. So our main findings was the Vive was the most accurate system for hand location across all hand location measurements, the horizontal, the vertical, and the lateral. It had an overall error of 13.7 centimeters, and it was as low as 8 centimeters for the horizontal distance, which for ergonomics, as you could imagine, is probably the most critical measurement, right? The further away if you're lifting a load from your spine, the worse that joint moment is going to be for you. And there's tools to assess that. So that's one we really got to hone in on and kind of study in the future. Is that, as I mentioned before, is that air okay for an analysis like that? So yeah, most of them were also more prone to error when the spine was flexed at far reaches. And the graphs show the error for the H, V, and L put together on the right side. So that's just kind of the overall error for all of the conditions. Limitations, definitely we only use one-armed reaches for this. There's definitely some potential noise when you're running all three systems together. Real-time body tracking is displayed from the Vive trackers, so that's kind of like that was Siemens running their own model with the Vive trackers, so kind of like they're in real time that they built their model with the Vive tracking coordinates. So the VR model that's being produced in the Process Simulate video you showed was from the actual Vive trackers connected to the Vive HMD. So we only evaluated this, the Siemens Process Simulate product, because this is what we use for all of our assessments at General Motors. It would be nice to compare software like the outputs from other packages that exist out there. So again, we use the Process Simulate skeleton model, and we need to look at the raw data from each of the three systems. The Vive trackers would be hard to do. We'd have to get that skeleton developed from Siemens, but the XSense and the Vicon model, we could surely do that and compare them to what the Process Simulate model was producing. A related study which might interest people a little more that are looking at like the human factors of using VR. So for example, if you're doing a VR task and you look at that task in physical reality, kind of what behaviors kind of changed, or did this object end up where it was supposed to be? So on the table. So we're looking at that as well. The data is not fully analyzed yet, but we did the VR task, right, with all the markers on. We use that optical marker data set again to get the ground truth, and we are replicating that task in physical reality. So as you could see in the bottom diagram here, that person is putting the cylinder on those targets. So we just measured the deviation away from the target compared to the actual ground truth measurements. Fairly consistent between doing a task in virtual reality compared to the physical reality. The VR, for in this condition here, for the horizontal distance, the VR overshot it by only about 8.3 centimeters. Pretty good results when you consider, you know, you're holding a controller and you're not using like a capable glove. You're holding the Vive actual stick and trying to represent that cylindrical math object in the scene. So we're pretty happy with those results. Very good agreement for vertical and lateral. Actually, it was almost dead on for the heights of placing it on the tops of the tables and then moving it from side to side. There was, like I said, very good agreement, and the participants could generally place their hands in the exact same position and locations when they were in VR and PR, except for that horizontal distance. That's where we got the 8 centimeters of error, or being off target. So conclusions and next steps, just wanted to kind of cover that body tracking with VR immersion provides reasonable representations of the hand locations and could definitely provide good information for our ergo risk analysis. Additional work definitely needs to be to improve the estimates as far as when we're bending forward with spine flexion. And we want to quantify this error, right? So if we are maybe 4 or 5 centimeters off, could that affect making a decision from a job being red to a job being green? Meaning, I talked about that load being away from the body. What would that do to spine compression if we're calculating it, or the joint moment? So we're trying to put these in a bucket. If we're, say, Maybe it's 3 centimeters. We don't know exactly yet. We're going to do some additional studies to look at how much, say, something like compression would change or joint moments, and try to quantify if we're doing a VR task with this body tracking, can we use it to make decisions as we go forward? Also, just examine how incorporating gloves will affect the accuracy. Again, we're using those controller sticks, just basically your Vive Pro Eye accessories. Here you can see a photo where we have been testing the Manus Quantums, and we want to look now, if I am doing a complex reach analysis, what changes compared to, so for some tasks that we evaluate, if I got to push something with my finger, like a push pin or route, or actually forcefully grip an electrical harness, how does that change the horizontal distance? And could we even be more accurate when we're actually, touching, getting haptic feedback, and grabbing the parts and moving them how you would instead of waving a vertical controller? Yeah, that's all I had. Just wanted to show you kind of I'll let this video play while we go through questions. This is our current process. You can kind of see in real time. Still a little bit glitchy. This is process simulate, and that would be someone being fully instrumented. So we're using the Vive trackers here with the Manus gloves actually, and we have this posture monitor that's monitoring kind of torso angles, wrist angles, and what we'll do as we build up the car in these virtual type builds, once we know we're getting decent accuracy and we know that that level of air is okay to work with, we can use this as a screening tool live as we build up cars in stages like 4 to 5 years in advance. So that's that kind of like dialog box, that module that's running in the center. We put in red, yellow, green zones, and we're able to monitor the joint angles and some other risk analysis tools. Thank you.
Darren Bolthouse, Lockheed Martin. Just curious, you did the comparison of, the motion capture to the, I guess, gold standard, like what reality is.
Yep.
Do you see any opportunity to use that to like train a model and then maybe do like real-time AI posture correction based on the
Great
trained
question.
model?
So actually Siemens Process Simulate has just released a tool called the Motion Library. And that's stuff we've done in the past with static postures. So like these starting points for the 2D, moving your mouse around, like I said, trying to predict a posture, we would save these starting points for the eye shaft or a door install or a certain harness, right? Kind of like these consistent, regular parts, maybe there's 30 or 40 of them that we have to check on a new car each and every time. So this motion library, now we're able to save like these, we could act out the operator doing something. Normally you would call the plant that's built the same truck for like the last 20 years, but now with EVs, they're totally changed. So we'll be able to kind of act out something in VR or motion capture, save these 10-second clips and string them together. We're also looking at using some of the technology to kind of use now machine learning. So if we develop this massive library of VR teaching or these VR tasks, we'll be able to leverage that. So definitely, I think that's a great point, and there are some modules that we're going to be able to leverage in the future. Even operator videos, right, of current jobs today, can we use those motions or bring something out to the plant and get them back digitally to reuse those postures as well?
I'm Corey Smith from Axiom Space. We do a lot of human factors and ergonomics assessments. I'm wondering if you've done any research over using the Vive trackers and IMUs in the same simulation.
And what the Vive trackers?
So camera positioning tracking.
So what would be the I guess the outputs you're looking for? We've done that here with the horizontal vertical measurements, but what would you be looking at if you're comparing those two? What would you be looking for?
Essentially being able to use the main camera points on like the feet and the waists, and then of course the controller for the hands, and then using the IMUs for the lesser needed like elbows and the knees is what we're looking into doing.
The Vive, as far as the Vive trackers go, it's just 6 trackers, right? Pretty inexpensive. Like the trackers, I think, are $100 each. As I said, you won't get the best fidelity, especially for like the lower limbs and back, as you would compared to IMUs. But it's pretty good for, and you could see for the hand location specifically, it performed the best within that software we were looking at. Hopefully, I'm not sure if I'm answering your question, but.
I was just wondering if there was any benefit to combining both technologies into simulation as opposed to just sticking with one or the other.
Say that again,
Sorry, so like, is there benefit to combining both at the same time?
Oh, combining them at the same time. Not really, because if you're in a lab, we can position like 4 or 5 of the Lighthouse cameras. I don't know that it would make sense to do them at the same time. However, we have kind of double tracked a subject in the scene where we're using a different type of software that's already leveraging the Vive for the head mount display. And then we will track with XSense to actually bring that data into another software. So if you want to double track and look at one side of things might be, okay, that's my vision analysis and I'm kind of building up the car or looking at, the point of view of the operator, but then I want to stream the real motions into a different software. We have looked at that. So that would be the only time I would double track and use both of them concurrently.
All right, thank you.
Thank you, Ryan. So we have a break till 4:45, and then we have one more panel, one more case study, and you have a cocktail hour at 6. So please drink.